Okay, so welcome everyone for this November SIPTA seminar, and for this session of November, we are very happy to receive Alessandro Antonucci. So without further ado, I will hand over the mic to the chair, so to Kike, that I think has some slides, which is a new thing, I think, which is cool, and then we will let Alessandro tell us everything about causality and Credal networks.
So yeah, welcome everyone. So we are very happy to have Alessandro Antonucci today. He's, well, as you will see, a wonderful speaker. All of the people who know Alessandro know he's also a very nice guy and a wonderful person. So just, well, a summary of who is Alessandro for those of you who are not familiar with his work. Well, he got a master degree in physics by the University of Milano. Then he got a PhD in computer science at the University of Lugano in 2008, I think. And then at the moment, he's a senior lecturer researcher at SUPSI. He has also been doing a lot of research on many different topics, mostly on the field of Credal networks. In particular, he has been doing work on machine learning, on classification, on causality, on imprecise Markov models. He has more than 80 papers included in Scopus. Not only he has been doing theoretical work, much of his work has been done in applied projects. For instance, he has projects with Arma Swiss, with CTI, Stuyent or InnoSwiss, and only with the projects where he's been the project manager, because he's also been a team member in many other projects, he has been funded with over 2 million Swiss francs. So you may wonder that, okay, he's doing so much that, okay, must be like a kind of a shitty work that he's doing. But actually, this is not the case. He's getting the Best Paper Award at several conferences, also Best Poster Award. And not only that, but he's also been getting a Best Teaching Award at his institution, at the SUPSI. So, well, at this point, I think there is no more objections that anybody could be doing with respect to Alessandro's suitability here. And then we're very happy to hear what he has to tell us today.
Okay, guys, if you check the title of my talk in the presentation, it was a structural causal model R brackets solvable by Credal networks. So it was not a question. I removed the solvable by, and I am asking myself in this version of the title a question, which is structural causal model R Credal networks. And what I'll try to do during these 45 minutes, something like that, is to say yes. Somehow we are, I'm an imprecise probability guy, and it is very appealing to intend the causal model described according to the PERL approaches, structural causal models based on graph, as imprecise probabilistic graphical models, and to understand causal inference in a generalized sense as an imprecise inference and in an imprecise probabilistic graphical model. This is a joint work with Marco Zaffaron. Marco Zaffaron is currently the scientific director at ITSIA, the institute where I'm a senior lecturer researcher. And this work was done also together with Rafael Cabañas. Rafa was a postdoc at the time. This is something we started already 3 years ago. We are still working a lot on the topic, but originally we started like 3 years ago. And I think everything started from the intuition of Marco about the relation between partial or non-identifiability in causality and imprecise probability. Basically, the lack of information at the latent level, at the exogenous level in causal models can be intended as a form of imprecise probability. So I think it's a very nice and very intimate connection between two somehow different worlds. And if you want, this is an example on how imprecise probability theories can be used as a tool to be applied in a different domain. So we are not really making any relaxation of assumption about the models or whatever. We are just using Credal networks theory as a tool to answer causal queries. So this is one of the points of my talk. You can see there is a QR code if you want to just need the slides. I think later on they will be also online. Give me just a second to share. I have a link besides the QR code. I think I would like also to share the link, but it is complicated, so I'm not sharing the link, guys. Please just use the QR code if you manage to scan it very quickly. Otherwise, I think we can just start. But later on, you will access to the slides. Okay, I'm not really using this slide. This is just to show you where we are. I don't know if you can localize these red dots. There is a map of Switzerland, and we are in the very southern part of Switzerland, very close to the Italian border. We were used to be a small artificial intelligence institute. We have been founded 35 years ago. At that moment, nobody was really caring about artificial intelligence. You know, now artificial intelligence is booming. We are growing. I'm not spending that much no more time about ITSIA. Maybe some people in Imprecise Probability visited Lugano, visited our institute. We organized an SIPTA conference. If you are interested in this battle of scenario, which is an artichoke-made drink, come to Lugano, come to ITSIA, visit us, and I'll let you know about this drink. Now let's really start, and let me start by framing a little bit this talk. Can you see this red arrow? So I wanted to localize, in a sense, the topic of this talk with respect to different theories, also in a temporal scale. Everything about time here is very imprecise, is very generic, but just to give you some coordinates. So somehow we are talking about graphical models. And one of the first and one of the most important example of graphical models, directed graphical models, is Bayesian network. Bayesian network, I cannot say that have been invented in the book of Judea Perley in 88, somehow also 84 earlier. But let's say Bayesian network have been formalized by Judea Perley in this very important book. And Bayesian networks are an example of directed graphical models, and they are used just for the specification of joint probability distribution in a compact way. The graph is just a model of the independence relation, and this allows to define a global model by means of local pieces in a tractable, in a compact way. This is basically the idea, the general idea of graphical models. At that time, Bayesian networks were mostly used to implement expert system, to have a mathematical model of knowledge. And now we are on the top of this scheme. Now let's move down and let's talk about late 80s, the 90s, something like that. And if you are somehow related to SIPTA, you know that at some point in the history of uncertain reasoning, let's say like that, people started to consider generalized version of the traditional probability theory, not only after 88 and not only in the 90s, but especially at that moment, people started to be not completely happy with classical probability theory and to define and to invent a new formalism. Of course, we are familiar with the imprecise probability theory. We are familiar with Wallis' seminal work and seminal book. And at that time, after the specification of Bayesian network, some people, and you can see here, Fabio, people very close to the SIPTA community, Fabio, I think is also in the audience, Marco Zaffaron, they tried to extend graphical models, models like Bayesian network, to imprecise probability by basically replacing the local probabilistic parameter with sets of distribution. And this was the idea of Credal networks. So basically they started to specify Credal networks as generalized Bayesian networks based on Credal sets. In the same moment, people from evidence theory, from Denster-Schaeffer, they created evidential network. People from possibility theories started to define possibilistic network. So all these generalized probability theory have been applied to graphical model, especially with the focus on the reasoning. Now let's move again up And let's observe as people working in graphical models in traditional with Bayesian network started to apply these pure probabilistic models to causal analysis. And to implement causal analysis, as we will see, traditional Bayesian network might not be enough. You need more tools to move in this direction. To, for instance, identify the causal effect of some action, of some intervention, to find the causal strength of some variable with respect to some other variables. Bayesian networks are not enough. This is the book, which is just the summary of a lot of work of a lot of researchers. This is the book of Perle, and this is just for me an example of, involving what we call now the do calculus. And the do calculus is a procedure to answer basically causal query in Bayesian network with some additional information. So I want to say just that the research, we moved on the top, we moved from Bayesian network to causal models, and eventually, and now you can move to the right side of the screen. These are two relatively recent books, again, from Julia Perle, and especially the one on the right, the Book of Why, is an interesting non-technical reading. The causal inference statistics is a technical but very accessible, very, very good if you're interested in the topic reading. They started to focus on a somehow more general class of model called structural causal models. And here the goal was to answer any possible causal query by means of this system. But we are still on the level of graphical models. So we are still in the same field. What about the red arrow? I mean, people started to work with Credal networks to define Credal networks like the 2000, but then research moved on. We have new algorithms. We have a lot of experience in developing inference algorithms for this model. And eventually, I would say like 3 years ago, we managed to find a strong connection between structural causal models and Credal networks. And this is basically the topic. So, you know, in the sense, the two directions for a moment, they proceed on two parallel directions, and eventually they are kind of merging. Still at the application level, again, we are really using Credal networks as a technical formalism for causality. Okay, I will be very short on this slide, and this is just to say that I am an AI person. I work in AI since many years. And as you know, of course, even if you are not in AI, AI is booming. But let's say in the last 8 years, something like that, deep learning is booming. Machine learning based on deep neural network is booming. This is great. There are lots of super nice applications. But the kind of applications you can implement with deep learning is basically based on correlation. You are making very accurate prediction because you have a huge amount of data to learn very accurate correlational model. And this makes your prediction very, very effective. This on the left, on the left side of the slide, you can see a paper. Now it's a bit old, the paper. It's like 2018, if I'm not wrong. And this paper by Adnan Darvish from UCLA was trying to emphasize as the big achievements of deep learning are somehow related to sensing. We have very good results in computer vision, in speech recognition, and whatever. And this is basically telling us that what we call speech recognition, what we call human vision, is a complicated function, but we have enough data to approximate this function in a very accurate way. So we have very good technology for computer vision because we have enough data to obtain good approximation. You can prove that a deep neural network is a universal approximator. So somehow it's not that surprising that we can find a good approximation. What was a bit surprising that we managed to gather enough data to achieve such a level, and we managed. So, and this was 5 years ago, something like that. Okay, now we have large language models, and what large language models are telling to us? probably they are telling to us that even what we call natural language is not such a complicated function. So by only using a correlation, we can produce a very, very good text synthesized by algorithms, by these generative models. The point I would like to emphasize by this slide is that we can be even more ambitious. So artificial intelligence, and I will say science, has to be more ambitious. So we are very happy of using these technologies based on deep learning, based on correlation. But we should also try to use our approaches, our techniques to make a deeper understanding of the reality. And of course, we always say that causation is not correlation. So by this model, we have just a partial understanding of the reality, and we can do more. And to do more, okay, you can shape, let's say, the task, the different task by using an image like this one. And this is very famous, is from Judea Pearl, and it's like to have different levels of knowledge. And of course, the lowest level is the association, is about what you see. You observe something, and from a pure observational level, you can learn a correlation between objects, between the variables in your system. And this is very good for predictions. But this is not enough for all the kind of questions you can ask yourself. For instance, if you move to the second level, the first level is the level of machine learning, is the level of deep learning. But for instance, if you do something and if you ask yourself about the effect, the causal effect of your action, machine learning, the prediction is not enough. You need to move up, and it can be formally proved that to move up, the pure probabilistic model is not enough. You need some additional machinery to move to the second level. And the second level is the level of the intervention. This RL is about reinforcement learning. Reinforcement learning is agent taking actions, and is exactly in this level, in this domain. But even more ambitiously, you can try to ask yourself counterfactual questions. And counterfactual is about, if you want, imagination, but it's not really something esoteric. It's really just like to ask yourself, in the real world, I got this observation, I got this observation for this variable. I ask myself about what would have been in a different situation where this variable observed in this state would have been different because of an intervention. So I'm simultaneously considering the real scenario, the reality I observed, and having an alternative one. This is counterfactual reasoning, and we need dedicated tool. We need to develop a dedicated tool to face counterfactual reasoning. And basically, my point is that we need structural causal model, and to make inference, to collect answer from this structural causal model, you can use a Credal network inference. So this is just at a very global level. So basically, my point is that we need the Credal nets as a technical tool for counterfactual inference, which is on the top of this ladder of causation. Okay, so this was on the general level. Now, I'm using this slide, which has a minimalistic structural causal model, a minimalistic example. I have a single observable variable. I call this endogenous, and I will show you a single exogenous variable. It's the smallest structural causal model I can invent. But if you get this example, I will be very happy. I think you will get most of the message of my talk. So let's invest a bit of time on this super toy example. And let's say that, okay, we have a variable, let's say is Boolean, just to make things as small and as simple as possible. This is what I call a manifest variable in the sense, or observable variable, if you want, in the sense is a variable I can observe. Is Boolean, and let's say that I managed to collect data of observation about this variable. I know that you are very good in super complicated scenario for statistical learning, But let's say that my data are complete. There is our IID, everything is super simple. I'm, I don't know, frequentist, and then I do some trivial statistical learning, or I'm Bayesian, but I can use some uniform prior because it makes sense. But let's say also I'm an imprecise guy, I'm Bayesian, imprecise, I use the imprecise Dirichlet model, but I have a lot of data, and all these approaches, eventually they give me the same answer. And I know that the probability for one of the two options, the zero option of the Boolean variable, is a number, P. I can measure very, very, very well. And this is my probabilistic model, what I can learn from the data. I can use this model for predictions. Let's say this is about tossing a coin. I want to bet on, and I can use this statistical information for my betting. And maybe this is very useful. Data are telling me that the coin is biased, and maybe because of that I can make a lot of money because of this information. But we are still on the first layer of the ladder of the 3 levels of causation, because we are not considering a deeper, we are not moving in the direction of a deeper understanding of the phenomenon. We are just recording observation and learning probabilities. Can be very good for prediction, can be very good to predict the next outcome of my coin, but it's not about a real understanding of the reality. For a real understanding of the reality, let's do something else. So let's say that there is another variable, a latent variable. So a variable that maybe, at least for the moment, we cannot observe. And my terminology is endogenous for the X variable, the variable I can observe, and exogenous for the U variable, the variable I cannot observe. Let's say that for some reason, the U variable has 4 states. And okay, this is nothing. This is really just adding a new variable with no relation, but there is a relation. And there is a stronger relation between U and X, because basically X is a deterministic function of U. So my function f is deterministic, and if I know U, I know X. In this example, which is pointless, I have 4 states. The first 2 states of U are giving me X equal to 0, and the last 2 states of U are giving me X equal to 1 for some reason. In generally speaking, what I ask to my function, and I call this function also like the structural equation of my system, because there is a deterministic link between the two, a structure. What I ask from a mathematical point of view to this function is to be a surjection. So basically it means that for each state of the output, for each state of X, there should be at least a state of U giving me this output. But the function is not necessarily, and is not an injection. So it's not that I can invert. You see, the map is many to 1. I have the first 2 states giving of U giving the first state of X, and the last 2 states of U giving me the second state. So I cannot invert the equation. What is this reflecting? Okay, it's just reflecting a mechanistic situation. And if you want a mechanistic interpretation of the reality, I'm assuming that what I'm observing is the result of a deterministic process. I know that there are limitations to the deterministic view of the reality. We are not in Laplace in the 18th century, but okay, to some extent, let's say that this is quite realistic to some level of approximation, to some scale, to assume that what we observe is a deterministic function of something else, and in this something else, there might be quantities that we can observe, and there can be also latent quantities. And this is the reason of the probabilistic model we have over X. We have a probability over X for the simple reason that we cannot observe U. So as we marginalize U, we remain with an uncertainty. about the state of X, because eventually we are uncertain about the state of U. And mathematically, this is, if you want, is just a total probability theorem. So I'm just saying that the probability of a state of X is just the sum of the probability of a state of X conditional to the fact that a particular state of the latent variable is the one weighted by the probabilities of the different latent states. But the conditional probability of X given U under the structural equation assumption is a degenerate probability, because we have a mechanism. So our probabilities are degenerate. They can be 0, 1. And so basically this conditional probability is a delta function, which is 1 when X is exactly the output of the function f for the value U, and 0 otherwise. So I have this relation. I have the fact that P of X is a combination, is a linear combination, but the weights of the combination are the delta. So basically only 0 and 1s, and is a combination of different values of U. And this basically means that, okay, X is a deterministic function of U, but I also have a map that basically propagate the uncertainty on U to X. As when I am uncertain about the states of U, by this one-step propagation, I got the uncertainty about X. But the reality of this example, when I'm doing the statistical learning from X, is not in the direction of U, from U to X, but I will need something from X to U, because I'm starting from the statistical learning, and the statistical learning is about X. So the problem we might ask ourselves is whether or not it's possible to back propagate the uncertainty about X back to U. So basically to reverse the relation I just wrote here. And of course, it is not possible. And it is not possible because the structural equation cannot be inverted. It's not an injection. But you can do that in a generalized sense, in the sense that, okay, we have an observation, we have the data, and we have a single probabilistic model over the X. If we use the deterministic relation to back propagate, we will eventually obtain a set of models, of probabilistic models over U. In this case, the computation are very trivial. If you can see here in gray on the top, the P of U, I parameterized with P these models, but any specification of this P of U will reproduce the Boolean, the distribution on P of X. So if you want, this is already a Credal set specification. So you see, this K of U is a set of distribution, and basically is the set of all the distribution over U that are compatible with what we can observe. And what we can observe is the P of X. So this for me is a very, I would say that is the first example in which we don't need any additional assumption or generalization to introduce, let's say, imprecise probability. Okay, the assumption we need is the fact that U is a latent variable, but all the rest, if we assume that the structural causal model is based on this relation, we should accept that any distribution in this Credal set is a compatible one, and we have no way to say that one of the elements of this Credal set is more likely, is a better model than another one. So we really need the Credal set, and if we really need the Credal set, what we have here is a graphical model with some local model which is imprecise, and I will call this a Credal network. So in this sense, this is the simplest structural causal model you can consider, but this is also a very simple example of Credal network. Okay, I spent a lot of time now. Let me move a bit faster, and of course let me say that we are not interested only, and we are not at all interested in such a simple model. We are interested in models where we have a collection of endogenous variable and a collection of exogenous variable. So we need a more, generally speaking, we have a more complicated topology, and we call this model the causal graph to express the relation between the different variables. We assume that for each endogenous variable, we have an equation, and the equation is the way we determine the value of the variable as a deterministic function of the parents according to the graphical structure. The latent variable are typically assumed to be the root node, the parentless node in the graph, and the probabilities are only on the parent variables on this root node. So these are the exogenous probabilities are there. The problem is that these are latent variables, and generally speaking, we cannot directly assess the P of U. We can only assess the P of U by means of this back propagation, and this back propagation will make the P of U imprecise, will make the P of U Credal. So this is basically the kind of approach we want to consider. Okay, now let me just recap the 3 steps of the causal inference by a smaller example. Guys, give me a second that I see in the chat. Eric is always, Eric is asking whether the function is always multivalued, so it's never an injection. We cannot exclude, but I will say that in the interesting cases is multivalued. And in the interesting case, x is not only a function of the latent variable, but in the interesting cases, x is also a function of some other endogenous variable. So basically, generally speaking, you have different, let's say, different u giving the same relation, and so you cannot trivially invert the mapping. So this is just to answer Eric. Now let me be very quick in saying that okay, this is a 2 variable. I moved from the 1 variable example, 1 endogenous variable, 2 variable. The variables are taking aspirin, whatever, and having headache or not having a headache, whatever. Okay, I have data. This is a Bayesian network. I can use data to quantify the conditional probabilities, but using this conditional probability to say that, for instance, aspirin is effective because this probability is bigger than this is very dangerous. You might, using a pure observational probabilistic model to eventually have some causal statement can be very, very dangerous. And there are lots of paradoxes. This is one from the book of Pearl, but there are lots. So if you look at the data on the right, you may say that the more exercise you do, the more cholesterol you have. But this kind of inequalities, they can be different if you condition of some other variable in the system. So for instance, if you split the group of people with respect to the age, you will see that it's not that if you want to reduce cholesterol, you have to do more exercise. Very stupid example, but somehow useful to understand these kind of issues. If you move to the second level, so if you want to do an intervention of your system, basically is different because it's not that I observe that the patient got. I have some patients for which my observation is that they got the aspirin and some other they didn't. No, in this case, I'm interested in evaluating the effect of giving them the aspirin, and this makes things different. From an observational point of view, I just have the variable. But from a causal model perspective, if I give the aspirin to the patient, basically it means that there is no anymore equation. So the equation is replaced by always having aspirin. And so I have a different model. And this machinery, this change in the structural causal model is a surgery. And once you did the surgery on the graph of the causal model, you can address your query as a standard probabilistic query. In some case, the query basically is like a Bayesian network query, and you can prove that your query does not involve the latent variables. If this is the case, you can say that your computation is identifiable. And there is a nice techniques, which is called the do calculus, which is a necessary sufficient condition to decide when you can do something like that. I mean, to decide when you can basically compute a causal query by only observational quantities without involving the U variables in your query. This is very nice, this is very powerful, but this is not always the case. There are situations in which you cannot do something like that. And if you cannot do something like that, basically you say that your query is not identifiable. You cannot reduce the computation of your causal query to probabilities, to the probabilities you can learn from an observational data set. And these are the tricky situations. And a lot of people, a lot of groups working in causal theories are trying to address this issue with partial identifiability or non-identifiability. Because in these cases, you can still say something. You can compute the bounds for the query, something that is very familiar for our community. I cannot say exactly what is the probabilistic effect of an intervention, but I can say that this probability is between this level, this lower bound, and this upper bound. And these are not related to our partial knowledge. These are intrinsic of the model. There are groups working by sampling techniques. There are people using polynomial programming. And there are people like us using Credal network theories. Somehow, we want to claim that our approaches are better for the simple reason that we work since like 20 years on a special class of optimization problem, which is exactly the kind of optimization which is needed by this computation. While polynomial programming and sampling are very, very general techniques, we already have a machinery which was designed ad hoc for Credal networks, but can be equivalently applied to causal models. Okay, so and the interest on unidentifiable queries and on partially identifiable queries is basically related to counterfactual. Counterfactual queries are typically only partially identifiable. Basically, the reason is that, okay, this is a counterfactual where I ask myself, in the reality, my patient got the aspirin and was still with headache or whatever. And now I ask myself about the alternative situation where the patient didn't took the aspirin. And I ask myself about the patient having the headache or not. For this, to describe such a situation, I need to duplicate the endogenous variables. So I have the endogenous variables in the real world that I observed, and they are the endogenous variable in the alternative world, which is the one I'm considering. These are called the twin networks, but I can quantify these twin networks because both the endogenous variables in the real world and the endogenous variable on the alternative world are linked to the same exogenous variable through the structural equation. And the structural equation, we assume they are the same in the two worlds. So we can do counterfactual inference, and we can basically reduce counterfactual inference with a standard inference in a graphical models. But we know that this graphical models is a Credal network, so it's not surprising for us that the result of the query, generally speaking, will be an interval. So this is basically the link, and this is the reason for our focus on counterfactual inference. Okay, this is somehow not something new. People started to work a lot in the last about 3 years, something really like 3 years, and people started to investigate a lot. But the first paper on partial identifiability is from '94. Okay, is an example, is a small example, was with Julia Perl and another person. They consider this example. I think this is interesting for people like us, because this is an example with 4 endogenous variables, Boolean, and they try to compute some counterfactual. There is an interpretation is 2 guys going to a party, having a scuffle or not having a scuffle, whatever. There is a well-defined structural model. But okay, basically what this guy managed to do in 94 is not surprising for us, because it's a solution of what we will call the Credal network inference by linearization. They managed to compute these bounds as a minimization and a maximization in a linear program. But what they do is very similar to what people in Credal networks try to do as a naive approach to Credal network inference, which is linearization. So my model is complicated because it's merging different distribution, and each distribution is a kind of optimization. Each probability is a kind of optimization variable. But if I consider the model jointly, it's not a sum of product. It's just a sum, and I can use linear programming. The obvious problem is that this linear program will be exponentially large. These guys in 94, they consider a very small problem. They managed to do all the computation in this relatively large, but not that large, was 4 Boolean variables, so let's say like 16 variables linear program. But this approach is clearly not scalable. And now let me try to show you what we did for this example, but this is a general procedure. So in this general procedure, what I'm writing here is a combination of marginal probabilities for the exogenous variable, the 4 exogenous variable, and these delta are basically the conditional probabilities that they generate. So this is the joint distribution of the model. I'm marginalizing out the latent variables, and after the marginalization, I have the model only over the endogenous variable. And this is the observable model. This is what I can compute from the data. So this constraint I wrote on the bottom of the slide is like a consistency constraint with the reality. And this is what is constraining the value of my latent variables. The problem is that this constraint is global, is mixing together P of UA, UC, UB, US, and is non-linear. In 94, Perl linearized the constraint by looking at the product of this probability as a single joint probability, but this is not scalable. What we can manage to do is to decompose this constraint into local, and by local I mean involving only single distribution of the single latent variable constraints that are also linear. And this is basically what we get. Is a kind of arc reversal procedure we implement. And by this procedure, basically, what we get is a mapping between structural causal model and Credal networks. And by means of this mapping, then we can address any query as a Credal network inference. So we can do intervention and then compute the lower and the upper bound by Credal network inference. We can do this twin network by duplicating the endogenous variables. The special case of identifiable queries is just a Credal networks giving you, as a result of a query, a lower and the upper bound which are equal, which might happen in some cases. And this is just a numerical version of what Perl implemented as symbolically as do calculus. Okay, let me just skip a little bit and just say that, okay, we have software for that. And this software is really just a mapping of the causal query to Credal network inference. We had some library for Credal networks, and we are just mapping the two approaches. This I don't want to skip. I will be very quick on this. Is just to say that, especially if some of you is familiar with Dempster-Schaeffer and stuff, these are basically constraints on the P of U, because on the left-hand side you have numbers, and these are the kind of constraints you have with belief function. If you intend a belief function as a special class of Credal set, which is not all people working with belief function is doing, you have this kind of constraints. And basically what I want to say is that the Credal set, the kind of Credal set you get in these models are, not surprisingly, with people familiar with this kind of model, and maybe this has something to do also with the question of Eric, are belief function. what I should say is that we are not exploiting this fact. It's very nice, it's very beautiful, but we are not taking at the moment any advantage. Maybe we can do some choquet approach. And let me also mention that people like Fabio Kozman and Dennis Mawa are working a lot in a probabilistic logic, which is different, but there are many analogies because they have, a logical relation. So they have, which is something like our structural equation. They have, some case, uncertainty on the atoms, and sometimes they have just no information. So people like Fabio and Dennis, they proposed some Credal probabilistic logic. And basically the situation, the purposes are different, but formally there are lots of analysis, and also they have results about their Credal set to be basically belief function. So a nice challenge for this community will be also think whether it's possible to take advantage of these results. Then let me say that the mapping to Credal networks is trivial for some topology, is doable for some not so special, but with some constraint on the topology. In the very general case, if you want to do the same, you have to merge together latent variables. But if you merge together latent variables, the size of your problem might increase exponentially. So basically, we are not done with the mapping to Credal. So this is not enough to practically solve. Is a general result in terms of representation, but in practice, you need something more. I'll be very quick. I think I skipped this. This was an application, but I wanted to mention to you that what we did after the Credal network mapping was how to solve the Credal network inference in these more generalized setups, and what the solution we managed to find is based on EM, is what we call a causal EM. Let me just mention the intuition. Basically, we have observation about the endogenous variable, about the X. We don't have observation about the U, but we can use an EM procedure to complete this observation. And generally speaking, the issue is that the EM is known to find the maximum of the likelihood, but as we have missing data, it might be that the likelihood has many maximum, and the EM is only giving you a solution on a local maximum. But it's possible to prove that the solution we get is on the global maximum. And to be on the global maximum basically it means to be consistent with the data you observe. And basically this means to give you an inner approximation of an inner point of the Credal set. And in this way, basically, we can approximate our counterfactual inference from the inside. It's an inner approximation of the counterfactual inference. And we have some result, let's say some credibility interval, proving that with relatively few, because we have to run many times with different initialization, and in this way we can obtain a very, let's say, accurate inner approximation. I skip a lot about this stuff. Let me just say that now we wanted to further speed up the inference, so we are using some techniques from knowledge compilation. We are working with people at UCLA to speed up the inference part. Because we need to run this EM technique multiple times, so we use probabilistic circuits for to speed up this part. And something just really did finished 2 days ago with my student. We are using, as now everybody in AI is using a large language model like GPT. And we are using GPT to parse the causal graph, because you see, for this kind of modeling, the first step is to parse the causal graph. So we are focused on medical domains, and we ask GPT to parse the text of medical abstract and to extract a causal graph. Is this relevant for people like you? Not directly, but this is part, because by these techniques, generally speaking, you don't get a single graph. You need a collection of equivalently okay candidates to be a causal graph. And now a lot of people is trying to investigating and to compute counterfactual inference with respect to the partial information about the latent variable and also the partial information about the structure of the causal graph. So generally speaking, it can be difficult to exactly know which is the causal graph. And this is another situation, another condition of ignorance that is familiar for people like us. It's like we don't have any second order information about the different graphs. It's not that we have to average the result of the causal inference for the different graphs weighted by the probability of the graph to be the right one. We have just to take all of them, which is exactly the same setup for imprecise probabilistic approaches. So I'm done. I hope you got this kind of connection, and also got as an example. I think there can be many others of techniques we people working in imprecise probability are very often considered very complicated and very deep, not in the sense of deep learning model. And this, in some other domains, can be a big advantage for a deeper understanding of the theory and give you stronger tool to address the problem. This was my experience in this field. I'm still working a lot. I hope to have also new results in a close future. Now we are working on canonical models, which is like enumerating all the possible deterministic models just to have structural equation. When we don't have a structural equation, we are interested in continuous variable. This was for discrete. We are interested in explainability based on counterfactual. I will try also, I'm running many times a standard EM, but it would be also appealing to propagate a Credal set according to an EM scheme, which I still don't know how to do, but this would be very, very appealing. So guys, thank you for your time. Was 50 minutes, maybe too much. And now, if you have, I will be very happy to answer your question.